Hello learners, welcome to Unacademy. So just give me 1 second, let me quickly check if I'm online. Okay, so in today's class we are going to learn about what is work, how do we see, and then we will derive a formula for work done. Okay, and we're going to cover some concepts from work, energy and power unit. Alright, so before we begin, my name is Mohana. I'm a physics educator here at Unacademy, and this is my Telegram channel link, so you can follow me through my Telegram channel, and this is the common ICSE and ISE both channels, so you can follow this channel as well. Okay, now whenever you say what is work, right? So if work has to be done, there's two things that has to take place. A force should act on a body, and for the applied force the object should also move through a certain distance. Alright, so over here if you see, okay, so over here if you see, imagine a weight or an object that is getting pulled, right? For the force applied, whenever a force acts on a body, the body moves through some distance, and if you look at the distance in which the object is moving, it would actually move in the direction of the force, right? So here the people are pulling the object, right? So the force applied is in this direction. For the force applied in this direction over here, the object's displacement is also in the same direction as in the direction of the force applied. So for work to be done, there are two things that has to happen. A force has to act on an object, and for the force applied, the object has to move a certain distance, okay, in the direction of the force. So condition for work done on an object is that a force acts on an object and the point of application for force moves in the direction of the force. Okay, then we say there is some work done. Alright, so if you see a horse pulling a carriage over here, right? So a cart over here. So as the horse moves, right? So what we see over here, there is a force that is acted on it in this direction, and for the force applied, see the displacement. For the force applied, the carriage was initially here, but as the car moves, right, the carriage actually moves with the horse, and the displacement is also in the same direction. Then we say that there is some work done. Now also if you see what is the work done by the engine, the engine is applying a force on the carriages, and the carriages actually move along in the direction of which the engine is moving, right? So there is a force exerted by the engine on the carriages, and that is basically, again, some work is being done here. Or even if you see a person climbing up the hill, right, what we see over here is another example of work done. Now if you look at work done, right, you're applying a force and the object moving through some distance, and that we call it as work done. So this, if you see, the first concept what we're going to see is work done by a constant force. That is, as the object is moving through certain distance, the force applied at all points were same. That is, for example, let's say this particular block, we are applying a force to it, and for the force applied, okay, the block moved from this point over here to this point, right? So this is the displacement, and if you see, the force applied was in this direction. Now if you see, for this particular force applied, every point throughout its motion, right, what we are seeing is, let's say for example the force is around 15 Newton. Then from the start to finish, when the force applied is a constant force, that is 15 Newton. As an example, if you're taking is 15 Newton throughout, okay, that is the force acting on this object to move an object through a certain distance, then we call it as a work done by a constant force. Okay, so if you see in this case, the force is acting in this direction. So initially the object is, let's say from this, let's take from the center of the object was in this direction. So when the force acts on it, right, the object gets displaced till here. So force acts in this direction, and the object's displacement is in the same direction as the force. Okay, the object moves in the same direction as the force, right? Then we say work done is nothing but equal to force, the applied force, into what is the distance moved, okay, the distance moved by the object in the direction of the force. So in this case, work done will be nothing but equal to force, okay, times the distance moved in the direction of the force, right? So this distance moved, we have taken it as S over here. So over from here what we see, force is equal to, okay, work done is equal to force times displacement. Okay, now this is basically the case. This is the equation we use to measure work done when force acting along the direction of the force. But if you see in most cases, right, the force applied and the displacement, they both could be inclined at an angle, right? They may not be may not be along the same line as earlier. Okay, so initially if we are saying this is force means, okay, displacement again being a vector quantity, the force is in this direction means displacement vector is also along in the same direction. Okay, but okay, angle between them is 0, right? In this case, force and displacement angle, if you see, angle between them is 0. But that may not be the case in most times, right? So actually, if you see what is if you see in this case over here, okay, the person pulls this particular the load over here, and if you see the force that is applied, okay, this load is tied to a thread or to a rope, and obviously tension force would act, right? As he pulls the rope, there would be a force acting along in this direction, right? So along the direction of the rope. So for this particular force acting, if you see, okay, the object is actually getting displaced, okay, in this direction over here. So force applied to displacement, they are actually inclined to each other, okay. They no longer the angle between them is no longer 0. So in this case, if you see, okay, in this case, if you see the force acting between these two objects, right, to find it, what we are going to do, let's take this particular, okay, for in this case, if you see, the object was initially over here, force acts along this direction, the object was initially at this point, and after some point we are seeing the object is somewhere around there. So this is the distance moved and this is the force applied, okay. So in this case, there is an angle component that comes into picture. So now if you see what is work done, okay, work done in such a case, so what we saw earlier, force was acting along in this direction, and if you see, displacement was along this direction over here. Okay, so now if you see, there is an angle theta, right? They both are inclined to each other with a particular angle. So here what we have to do in this case is, okay, we are going to calculate work done over here, okay, we are going to take the component of the force in the direction of displacement, meaning we are going to resolve this force vector over here, okay. So you can resolve them into its horizontal as well as its vertical vector, right? This is force acting along the horizontal direction or the x-axis, we can say, force acting along the vertical or the y-axis over here, right? So force acting along the x-axis and y-axis. Out of this, okay, we are going to take the force vector which is along the displacement vector. Okay, so we are going to take the component of force in the direction of displacement. In this case, the component is basically the horizontal component. Okay, to get that, what we do, we drop a perpendicular from this particular force and see where it meets on this particular line, and this distance what we have is basically here the component of the force in the direction of displacement, and into, we are going to multiply with that with the displacement. That is, what we do over here is we are going to look at what is the force applied, for the force what is the displacement, right? Especially with respect to the force, what we want the force that is in the direction of the displacement vector, right? So to find that particular component, what we are going to do is very simple. We are going to do a very simple trigonometry, right? We have resolved it into two vectors, right? Let's take this as fx and let's take this as fy over here. Alright, now what we are going to do, we have a right angle triangle. Okay, now we have a right angle triangle, this is force, and we have resolved it into two components, that is fx and fy. So from here what we can do, okay, we can move this vector to the other side, right, and we can move this vector to the other side, we get fy over here. Now if you see, the magnitude of all of these vectors gives us the side of this particular triangle, right? So what we want this particular component fx over here, right? So for that, now these two vectors are at an angle theta. Now fx vector is in the direction of the displacement vector. Now to find this vector, what we can do, we can make use of trigonometry. So we take cos theta. Cos theta is nothing but base by base by hypotenuse, or in other words opposite or adjacent side by hypotenuse, right? Adjacent side we have fx over here divided by hypotenuse, this side like this f. So from here what we can find, this fx over here is nothing but f cos theta. So in this point over here, fx, if you see, this is nothing but, this is equal to f cos theta. So the component that is in the direction of the displacement vector is nothing but f cos theta. So over here what we have the work done is nothing but component of force in the direction of the displacement, that is f cos theta, into magnitude of displacement s. Okay, so we can actually rewrite this as fs cos theta. Again, if you see, fs cos theta is nothing but cos theta come into picture, right? What we did over here, we took a component of the force in the direction of another vector, right? We took component of one of the vector which is in the direction of another vector. So this will basically give us a dot product. Okay, so from here if you see, you will get this as f dot s, right? Work done is nothing but f dot s. Alright, so why do we do that? Okay, so before we understand that, let's see which of the following vectors is following is a vector quantity. So we have work done, we have displacement, we have force, we have both force and displacement. Which of the following do you think is a vector quantity? Okay, just a second guys. Okay, so here if you see, both force and displacement are vectors, but work done is a scalar quantity. Okay, so both A and B, right? So what we have over here is force and displacement, which are vectors, and you multiply two vectors and the product you're getting, okay, the answer you're getting is actually just a scalar quantity. Okay, so work done is a scalar quantity, and force and displacement are actually vector quantity. So you're multiplying two vectors and getting a scalar quantity. So what we see over here is basically a dot product. Okay, so work done is an example of dot product. Now, so we know if force, so we have seen two cases. One is when force is in the direction of displacement, all we get is fs cos, just f into s. Why we are getting this is very simple also. Okay, so let's say the force is along the direction of the displacement. Okay, so if force is along the direction of displacement, then even if you take this formula, that is fs cos theta, so f vector is in this direction, right? The displacement is also in the same direction, so angle between them is basically 0, right? So if you see, cos of 0 is actually 1, so you will end up just getting force into displacement. Alright, now if there is an angle between them, you have to take force, magnitude of the component of force in the direction of the vector, displacement vector, into what is the magnitude of the displacement into cos of the angle between them. Okay, this gives you work done. Now, what are the units of work done? So in SI system of unit, we say work done is actually in terms of joules. So 1 joule, okay, 1 joule is said to be the work done. Okay, if you apply 1 Newton of force, and if you display an object, because of the 1 Newton force, if that displays an object through a distance of about 1 meter, okay, in the direction of the force applied, then we say that is nothing but, then work done is nothing but 1 joule. Okay, so if you see, 1 joule is nothing but equal to 1 Newton meter. Okay, so in this case over here, if you see, you are applying a force, right? So yeah, let's say you are applying a force. Let's say the force applied is around 1 Newton. For the 1 Newton force applied, the object got displaced through about 1 meter over here. Then work done will be around 1 Newton meter. Okay, or in other case, this 1 Newton meter is nothing but equal to 1 joule. Okay, so from here, okay, this is unit of energy. This is the SI unit of this is basically the SI unit of work done. Okay, what if you have what about in CJ system? In CJ system, we give it in terms of urges. In CJ system, we give it in terms of urges, and one urge, if you see, is nothing but if you apply a force of about 1 dyne. Okay, So let's say we have an object here and we are applying a force. So the displacement over here is from here to here, okay, and you are applying a force, okay, and the force and the displacement again are in the same direction. So the force applied in this case, let's say it's about 1 dyne, okay, and the displacement over here is about this displacement, this distance, displacement S over here is about 1 centimeter, okay. For 1 dyne of force applied, let's say the object moves through a distance of 1 centimeter, that is in the direction of the force applied. Then we say that is nothing but 1 urges. So 1 urge is nothing but equal to 1 dyne centimeter. Nothing but equal to 1 dyne centimeter. So okay, then how can we convert? So the conversion is very easy if you want to convert from joule to urges, right? So let's say we have 1 joule, the relationship between joule to urge over here is very easy. So let's take around 1 joule, right? 1 joule is nothing but equal to 1 Newton times 1 meter, right? So 1 Newton is nothing but about 10 to the power of 5 dyne, right? 5 dyne times 1 meter. 1 meter is about 100 centimeters, right? So that is 10 square centimeters. So 1 joule over here is nothing but equal to 10 to the power of 5. So power terms, base terms are same, you can add the powers. 5 plus 2 is 7 dyne centimeters, right? Dyne centimeters. So 1 joule over here is nothing but equal to 10 to the power of 7 urges. So that's the relationship between the unit of work done from CGS to SI system of units. Okay. Now, when you talk about the nature of work done, see, work done can become positive, it can be negative, or it can be 0 as well. Okay. So let's say you're applying a force, okay, and for example this horse is pulling the cart, right? So the force applied by the horse is in this direction, right? Let's say it's in this direction. For the force applied, the displacement, right, the displacement is also in the same direction. Okay. Now if you take the angle between the force and the displacement vector over here, because they are along the same direction, angle between them is 0 degrees, right? So if the force acting on a body has a component in the direction of displacement, then the work done by the force is positive. So here if you see, work done if you take is nothing but Fs cos 0, right? Cos of 0 is 1. So what we end up getting is basically a positive force. Okay. So angle theta over here, in case of positive force, angle theta over here will basically be less than 90 degrees. Okay. So even if this particular, even if you see like in the previous cases that we have seen, right? Let's say we have an object, the force is acting along in one direction and displacement is along another direction. Okay, it doesn't matter. Even in this place, if you see, if you take what is work done, it will be Fs cos theta over here. Unless and until this angle theta is less than 90 degrees over here, we will get work done to be a positive quantity. Okay, why? In this case, we are just taking the component of force in the direction of displacement. So this is basically, if you see this, this is nothing but Fs cos theta vector, right? So a good example of positive force will be a horse pulling a cart. Now, if this is positive force means, then what about a negative force? So if you see a negative force, very simple, okay, when can force become negative? So we have this particular equation where we are saying work done, okay, work done is actually equal to Fs into cos theta, right? Okay. Now think about it. If you're applying, if a force is acting, okay, on a body and has a component in the direction opposite to displacement, then work done is negative. So if this is force vector, displacement has to be in the negative direction. Why? Angle between them will tend to become 180 degrees. Cos of 180, cos 180 over here, cos 180 degrees over here tend to become minus 1. Now work done will become minus F into Sy, cos of 180 degrees is minus 1. So very simple. Let's see this person pulling this cart over here. Okay. So as he pulls the cart, there is a frictional force that is developed in the opposite direction, right? Force is applied in this direction, but there is a frictional force applied in acting in the opposite direction. Now, if you look at the work done by the frictional force, this work done is very simple. Work done in this case is nothing but what is the force of friction times displacement. Again, from here to here, the displacement, again if you see, the object's displacement is in this direction, right? Is along this direction over here. The object is getting displaced along this direction. Now, this force and displacement vector are actually opposite to each other. Okay, so when an object is getting pulled over a surface, when it's sliding over a surface, okay, then the force of work done by the force of friction on displacing the object, that would be a negative force. Why? In this case, angle between this force of friction and S, the angle between them is 180 degrees. If you supply that, if you write that as 180 degrees over here, work done will end up becoming a minus quantity, right? Work done will be a negative quantity in this case. So this is an example of negative force. So this is minus Fs cos theta. Okay. So then other type of work done we have is zero work. Okay. So let's say work done by force, if the work done by the force is 0, okay, and if the object gets displaced along the direction perpendicular to the direction of the applied force, such that work done by the object is become, okay, the force on this object, work done becomes 0. There is a force acting, object is getting displaced, but work done is 0. When can that happen? Very simple. When can that happen? We know this is Fs cos theta. When can work becomes 0 over here? Very simple. When the force acting itself is 0, okay, or the displacement tends to be 0. That is, a force is acting on it and the object is not moving. You apply a force and the object is not moving, right? It is at rest wherever it is. So displacement becomes 0, so work done becomes 0. Right. Another possibility that we have is this angle component becoming 0. Okay, so when can this angle become, for what angle of theta can work done become 0? Very simple. If theta is equal to 90 degrees, then what we have? We have Fs into cos 90. Cos 90 is 0, right? So work done will become 0. Okay, so in this case what we are saying, the force, and that is only possible if the force and the displacement vector are perpendicular to each other, right? So take an object that has a uniform circular motion, okay, or let's say an object is having is basically in a circular motion. So if the object is in circular motion, then what we see over here, there would be a centripetal force acting towards the center of the object, right? So if the object, let's say it's going in this direction, so as it travels around this direction, right, the centripetal force, let's say this is the radius of the circle, so but over here in this case what we see, for this particular given object, the force will always act towards the center, right? Centripetal force will always act towards the center, right? For the centripetal force at this point, if you see, look at the displacement, look where the object is going. If you're looking at the displacement vector over here, at this point the object is moving towards this side, right? So the displacement vector is along this direction, right? So now angle between them becomes 90 degrees. Now if you look at work done, we get Fs into cos theta. Theta is 90 degrees. Cos 90 is 0. So work done becomes 0. Okay. So work done by centripetal force is an example of 0 work. Okay. So this is about nature of these are the three types of work done. That is, we have work done can be positive, negative, or 0. Okay. So to sum it up in simple words, okay, if simple words, we know the work done is nothing but Fs cos theta. Now if force and displacement are along the same side, then angle between becomes 0 degrees. Okay, so theta less than 90 degrees itself, okay, work done will be positive. Then what will happen? Fs cos of theta will become 1. So we get a positive quantity. Next, what we are seeing, in case force is acting along one direction and displacement is along the other direction. Now angle, if you take angle between them is 180 degrees. Now work done, if you take cos 180 is minus 1, so we get minus Fs, that is negative work done. So for work done by a frictional force, okay, when an object is getting displaced, that is basically a negative work done. Okay, or for example, when you are applying a brake, and for the applied brake the car comes to a stop, right, the displacement actually is becoming 0. So in that case again work done tends to become negative, right? So because the distance covered tends to become 0. Now there is another point we can see, that is when force vector and displacement are along in the are perpendicular to each other. This is, for example, theta is equal to 90 degrees. When that happens, what happens? Cos theta is, cos of 90 degrees is 0, work done will become 0. So 0 work is done. Okay, this happens because centripetal force, work done by centripetal force if you take, is actually 0. Alright, so these are the nature of the work done. Now let's do one numerical. So if you see, a person is holding a bucket by applying a force of 20 Newton. Okay, he moves the horizontal distance of 10 meters and then climbs the vertical distance of 20 meters. Okay, can you find the work done by him? Very simple question. Okay, and just give me 1 second. Okay, so in this case, if you see, what are we saying? A person is holding a bucket, okay, and by applying a force of 20 Newton. So let's say a person is holding a bucket. So when you lift up the bucket, right, you're applying a force in this direction. This force is around 20 Newton. So in this case, there is a force applied on this particular bucket, on the bucket, right, by the person, and that is upwards over here, right. Now, if you see, he is carrying the bucket and moving a certain distance. So force is in this direction. Displacement, if you see, initially he was over here, right. See, from here he is getting displaced, right. So this is the direction in which he is tending to actually going, the displacement vector is, right, it's towards the right. So what we see over here, as he moves, okay, he moves a horizontal distance, right. I'm sorry, just a second, guys. Okay, so what we are seeing over here, he moves a horizontal distance of 10 meters, right. So when he moves a horizontal distance of 10 meters, what are we doing? What are we seeing over here? Work done in such a case, is nothing but equal to force F into S into cos theta. So when he is moving in the horizontal direction, okay, so let me take that as W1, okay, WH, that is work done in the horizontal direction, okay. So that is nothing but force is what? Force applied is nothing but 20 Newton into displacement is 10 meters. Cos of angle between them we just saw, is holding this bucket in this direction and his displacement is in the other direction. So angle between them is actually 90 degrees, right. Cos 90 we know is 0. So work done when he is carrying the bucket and moving in the horizontal direction is basically 0, right. Then what we are seeing in the question, then we are actually seeing, right, and then he climbs a vertical distance of 20 meters. For example, let's take it as him climbing a ladder. Okay, now think about the force. The force he is holding, right, the force he is applying to this bucket, carrying the bucket, is in this direction. And in which direction? Initially he was here, he is getting displaced, right. The displacement vector is also in the same direction. Now angle between them tends to become 90 degrees. Sorry, I'm really sorry. Angle between them tends to become 0 degrees, right? Because the displacement vector and the force is in the same direction. So work done, if you see, what will happen? Okay, work done along the vertical direction, right? So work done along the vertical, if it will be nothing but Fs into cos of 0. Cos of 0 is 1. So work done along the vertical, if you see, will be nothing but, in this case, along the vertical direction, work done will be force, that is 20 Newton, into the displacement that when he climbs a vertical distance, that's around 20 meters, okay, into cos of 0 degrees. Cos 0 is 1, right. So sorry, this is basically work, force is 10, right, force is 10 and force applied is basically 10 Newton and the distance he covers is also 20. So from here, if you see that 20 into 20, right, this tends to be 400, okay, 400 joules. Now we want to find total work done. What will be the total work done? Total work done will be work done along the horizontal plus work done along the vertical, right. Work done along the horizontal is 0, work done along the vertical is 400 joules. So the total work done by him is basically 400 joules. Okay, okay. Now that we saw this example, now let's see what will happen when the work done, when the force applied on the object, we are applying a force and the object is moving, but let's say in this case the person drags this load across this floor, but as he drags the load, right, let's say from this distance to this point over here, this point, let's take it as 1 meter, okay, let's take another 1 meter distance here, okay, let's take another 1 meter and so on. But every 1 meter, if you see, the force acting on it, this could be around 5 Newton, then this could be around 6 Newton, then this could again be around 5.5 Newton. In the next 1 meter, he could drag by around applying a force of 5 Newton. So, as he drags this load across the floor, what we are saying, he is doing some work, he is applying a force and the object is getting displaced. But if you look at the force applying at each point over here, that is varying, right? So, in such a case, what we get is work done by a variable force. Now, how to do that is very simple. What we are going to take, we are going to take a graph, okay, between the work done, okay, the displacement that I am taking it as x, okay, and the force applied, okay. So, especially force with respect to distance, at what point, basically looking at it, at a given point, what is the force, okay. So, f of x over here, right. So, let's say when he starts applying a force, let's take that as xi, okay, initial displacement, okay, from where he is moving, okay. So, this initial point where he is starting, let's say that is xi, okay. Where he stops, where he stops finally, this distance, let's say displacement final, okay, this is displacement final. So, this is the distance through which he has moved. For this distance he has moved, what we are observing on the curve over here, initially the displacement was small, then it increased, and then again he is trying to, up towards the end, he is applying a similar constant force. Right. Now, if you want to find what is work done, what we have to do is we are going to make sure, take all of under this curve over here, we are going to consider this area, and we are going to make sure this particular displacement curve that we have over here is broken into small elements, okay. And we are going to take a small surface over here, and let's name this surface, okay, this rectangular surface as A, B, C, D. Okay, but around this rectangular surface, okay, along this displacement of delta x. So, for him to move this load from x to xi to xf, right, from initial to final displacement, he could have moved around 50 meters, okay. But let's take a small displacement somewhere around here when he was displacing somewhere around, for example, 0.5 meters, okay. For about 0.5 meters, the force applied was constant, okay. So, now what we are seeing, we are going to break this down into such small areas, okay, and we are going to find what is the work done. So, work done in this case will be nothing but what is the force applied for this particular area times the displacement over there. For the small displacement, what is the force applied, okay. That is nothing but that work done will be given by this area of the rectangle ABCD, okay. For that small distance, we are actually finding this. Now, what we take, if we take summation of all of it, right. So, if we say that this particular force is divided into this particular work done, if we are taking it as, in this case we are looking at the displacement is taken at as small elements, okay. And if you say, so we are taking a small equal displacement under this curve over here, and we are saying, and if we take summation, okay, let's say all of this element is around delta x, and if we take summation of this value, right. So, then what we will end up getting, we will get work done will be nothing but sum of, okay, if you add all other such areas, then you will get work done will be nothing but equal to sum of initial displacement to final displacement, what is f into delta x. This is nothing but sum of all sum of areas of all rectangles under the displacement curve, right. So, now let's say we are taking for a very small duration, right. For example, we are taking limit delta x going towards 0 when the displacement becomes very small, okay. Now, the summation x of x into, from the initial displacement to final displacement into delta x will be equal to integrate within the limit xi into xf, right, f into dx. So, this basically gives you what is the area under this curve, that is, here we have the displacement versus force curve, okay, and this gives you what is the area under the curve, okay. Area, if you take force, what is displacement, area under the curve gives you work done, okay. So, this is how you calculate in case of work done by a variable force. Let's end this today's class with one simple note, okay, one simple numerical. So, let's say 3 kg particle starts at origin and moves along a positive x-axis, okay. The net force acting on it measured at intervals of 2 meters is 2.78, 3.52, 4.25 and 1.69 and 12.1 meters. What is the work done in this interval? What is the work done on the particle in this interval? Okay, so what they have done over here is very simple. So a particle of about 3 kg, right, a 3 kg particle, if it's moving, the force is applied to it and it's moving. So if you see how it is moving, the first 2 meters, the force applied to move this particle, to displace it around 2 meters, is around 2.78 Newton. For the next 2 meters, the force applied is 3.45 Newton. And for the next 2 meters, the force applied is basically 4.25 Newton. Okay. So this is for every 2 meters, the force applied changes. So this is work done by a variable force. So in this case, what we can do is, we can take what is work done, right? In this case, what we can do is, total work done will be nothing but sum of individual forces, right? What is these? I is equal to 1 to n. We can take it like this, or summation I, right? So otherwise, in simpler terms, what we can do is, we can find what is displacement for every case. So for the first 2 meters, the displacement is 2.73 meters, right? So the first 2 meters, the displacement is the first 2 meters, the force applied is 2.78, right? This is force times displacement, and we know it is moving along the x-axis. So for the force applied, it is moving along the x-axis. So the angle component over here tends to become 0. Okay, so this is force times displacement. Similarly, if you see plus, the next time if you see, this is nothing but 3.45 is the force applied, and the displacement is nothing but 2 meters again. So we can carry on doing this, or in much easier terms, how we can write is, we can add up all the force, right? 2.75 plus 3.45 plus 4.25 plus 1.69 plus 12.0. Okay, add all this and multiply it with displacement, right? Displacement is 2 meters. So work done in this case, let's see quickly. This is 2.78, right? So this comes up to about 24.17 into 2, right? So if you just double the value, work done in this case will be around 48.34 joules. So if in case variable force is given, what you can do is, depending on the question again, in this case what we can do, make sure you add up what is the total force acting on the system into what is the displacement. Okay, so for every 2 meters, the object was applied a force of 2.78, 3.45 and so on. So we have to multiply 2.78 by 2, 3.45 by 2. You can do that, or add all of them and multiply it with the displacement. Okay, so with this note, very simple. Let me also do one more question before I end. Okay, a cyclist comes to a skidding stop in 15 meters. Okay, during the process, the force on the cycle due to the road is 300 Newton and is directly opposed to the motion. Okay, so how much work does the road do on the cycle? Okay, very simple. The cyclist is moving and she comes to a stop. Okay, so if she is coming to a stop means her displacement might be in this direction, but if she is coming to a stop means what is happening over here, there is a force acting on this particular cycle in the opposite direction, because why? She is coming to a skidding, what we see from here, a cyclist coming to a skidding stop in 15 meters. Okay, so displacement we have over here is 15 meters, and if you see, the force in this case is basically the frictional force, because frictional force will basically bring the cycle to a stop, right? So work done in this case is nothing but F into S into cos theta. Now think about the displacement over here. Now force in this case is acting in this direction, and if you look at the displacement is in the forward direction, right? So angle between this force and the displacement vector is 180 degrees. So work done will be nothing but, okay, force in this case they have said the force on the cycle due to the road is 300. Okay, the road exerts a force on the cycle of up to 300 Newton. Okay, so we get that as nothing but 300 Newton into displacement over here is nothing but, from the question we saw, it is basically the displacement. She comes to a stop in 15 meters. So displacement over here is actually 15 meters. Okay, into cos of, what is the angle between them? It is basically 180 degrees. Right. So from here what we get, this is nothing but 4500, but cos 180 is minus 1. So we get minus 4500 joules. Okay. Next simple question, same question, okay. The cyclist comes to a skidding stop in 15 meters. During this process, the force on the cycle, okay, what the force on the cycle due to the road is basically 300 Newton, okay. Right, now how much work does the cycle do on the road? Okay, now according to Newton's third law, what we can see is, okay, whatever is the force exerted by the road on the cycle also exert an equal, but okay, but the force applied will be in the opposite direction, right? But it will exert an equal and opposite force on the road. So force applied by the cycle on the road is basically 300 Newton. Okay. So if you calculate work done will be Fs cos theta over here. But for this force applied, is the road going through any displacement? No. Okay. Initial case, what we said, the initial previous question, what we saw, that the force on the cycle